Right now, at opposite ends of this planet, two massive ice sheets that scientists once thought they fully understood are behaving in ways no one foresaw. What makes this so strange is that they are deteriorating at the exact same moment, yet driven by nearly entirely separate sets of causes. Up in the Arctic, wintertime sea ice has just tied for one of the lowest levels ever recorded since satellite observations began back in 1979. Over in Antarctica, a continent that for decades seemed almost immune to global warming taking place across the rest of Earth, has now slipped into a downward spiral researchers describe as genuinely unexpected. This shift is being fueled by a rare alignment of natural forces that scientists had never observed come together quite like this before. We have two poles, two entirely distinct physical systems, one ocean covered in floating sea ice and one continental landmass buried beneath thousands of feet thick ice. And both have recently produced readings that made observing scientists pause and double-check their measuring equipment. Stay with me. By the end of this piece, you will have a clear picture of exactly what is unfolding at our planet's northern and southern extremes, why seasoned researchers who have dedicated their careers to this field are calling portions of these developments unprecedented, and what all of this actually means for ordinary people living thousands of miles away from either pole. If you have ever wondered whether non-stop news headlines about melting polar ice are overhyped or represent a truly serious issue, this walkthrough lays out hard, real-world data without sensational noise. Leave a comment below and tell me which pole you believe poses the bigger concern right now, the Arctic or Antarctica. You may well change your mind by the time we finish. And if you would like to follow along as these stories keep evolving, hit subscribe so you do not miss future updates, because conditions on both fronts are shifting rapidly. Let's begin at the top of our world. The Arctic situation has the longest-running data set, and it sets the stage for everything else we will cover. Through most of the early 2020s, puzzling patterns started showing up in observational data. Arctic winter sea ice, the thick frozen cap that spreads across the northern globe roughly from October through March each year, had been shrinking for decades as global temperatures climbed, but somewhere around 2005, that long-term decline appeared to hit a plateau. Year after year, the winter maximum ice extent remained low compared to 1980s benchmarks, yet it stopped dropping further. When researchers plotted these trends, what they saw looked almost like stabilization, a pause within the decline that had persisted since satellite records started. Several scientists even published papers arguing winter sea ice had entered a holding pattern, no longer retreating as it had in prior decades. That interpretation stood for nearly 20 years. Then 2025 arrived, and that whole framework collapsed practically overnight. Between the winter of 2024 and winter of 2025, Arctic sea ice during its peak growth phase fell by almost 6% within a single 12-month span. To put that figure into perspective, this marks the steepest year-over-year winter ice loss documented across the entire satellite record going back to 1978. 6% might not sound dramatic on its own, but we are talking about an ocean ice expanse that normally covers roughly 14 million square kilometers. 6% translates to an area of vanished ice about twice the size of Texas, gone within just 1 year. What truly unsettled the scientific community is the timing. This should have been the calendar point when ice reaches its annual maximum, the time of year after months of Arctic darkness build up the thickest seasonal ice cover of the whole cycle. Instead, ice levels landed at lows unseen across nearly 5 decades of monitoring, precisely when they ought to be at their strongest. A research team led by scientists from the University of Southampton working alongside the United Kingdom's National Oceanography Centre ran computer simulations to test whether such a sharp drop was physically plausible under present-day Arctic warming trends. They compared real-world observations against decades of climate model outputs, searching for comparable events under similar warming conditions. Matching events were uncommon, yet they did exist. Critically, the simulations also reproduced another outcome researchers had not anticipated going in. During the following winter of 2026, total ice cover edged slightly upward off the prior year's historic minimum, a modest partial recovery. The computer models replicated that small uptick almost exactly. That may sound like encouraging news, ice bouncing back following a catastrophic crash. Yet researchers are very clear about what this minor rebound actually signifies. In every comparable scenario generated by the models, such a severe downward shift almost never fully reversed afterward. The system does not snap all the way back to its former state. Instead, it tends to settle into a lower range and oscillate around this new, diminished baseline for multiple years. In other words, the slight 2026 recovery was not the beginning of a return to old normal conditions. It was Arctic sea ice settling into a new, lower normal around which it will fluctuate. This distinction carries huge importance, and it deserves careful consideration because it directly contradicts narratives built around that supposed pause. For years, This apparent stability was cited, sometimes in good faith and sometimes not, to claim Arctic ice loss was leveling off, and that alarm over polar melting had been overblown. New research using concrete numbers makes the opposite case. That pause was never genuine stabilization. It represented a temporary lull superimposed atop a much longer-term downward trend. Once environmental conditions aligned as they did in 2025, decline resumed exactly where older trend lines had left off, just compressed into one dramatic single year instead of unfolding gradually. NASA and the University of Colorado Boulder's National Snow and Ice Data Center independently confirmed this pattern. Arctic sea ice hit its annual maximum extent March 15, 2026, at just over 14.29 million square kilometers, statistically indistinguishable from the 2025 maximum measurement of 14.31 million square kilometers. For 2 successive years now, the Arctic has registered the lowest winter peak values measured since satellite monitoring commenced in 1979. Scientists at NSIDC and NASA note these 2 years are effectively indistinguishable from one another, both sitting at the very bottom of our 47-year observational record. Jennifer Francis, senior scientist at the Woodwell Climate Research Center, likens this pattern to a warning flag from a medical checkup, a symptom that taken alone may not spell disaster, yet keeps reappearing across every test and consistently points in one troubling direction. When bodily metrics all start trending adversely at once, physicians do not wait for full-blown crisis before intervening. Climate scientists are making that exact same argument for the Arctic Ocean today. Why should winter season ice matter so much? When popular conceptions of the Arctic crisis center mostly on summer conditions, those well-known images of shrinking September ice and stranded polar bears. Winter sea ice performs a function summer ice cannot. It forms a barrier separating ocean water hovering just below freezing from overlying air that can drop 60 or 70 degrees colder during the sun-free winter months. Where this barrier is thick and solid, heat and moisture remain locked within the ocean. When it thins or develops gaps, heat escapes upward into the atmosphere all winter long. That extra energy does not stay confined above the North Pole. It reshapes atmospheric pressure patterns, feeds changes within the jet stream, and atmospheric scientists keep finding links between reduced winter Arctic ice and extreme cold outbreaks, plus shifted storm tracks thousands of miles south, across places such as the American Midwest and Northern Europe in midwinter. A thinner Arctic winter ice cap is more than just a regional statistic. It acts as a lever that can alter weather systems experienced by everyone living far to the south. The underlying mechanism here hinges on albedo. Once you grasp this concept, you will never view satellite imagery of polar ice the same way. Snow and ice are bright surfaces, reflecting most incoming sunlight straight back out into space. Open ocean water is dark. Dark surfaces absorb solar radiation rather than reflecting it. When sea ice disappears and gives way to open water, that patch of ocean stops bouncing sunlight away and starts soaking it up, warming the water underneath. Warmer seawater then makes it harder for ice to reform the next winter, exposing yet more dark open ocean the year after that, which absorbs still more heat. This creates a feedback loop, literally our planet's thermostat operating in reverse. It is one major driver behind the Arctic warming roughly 4 times faster than the global average. Each square kilometer of vanishing ice is not merely a symptom of warming, it becomes an additional cause of further warming. That explains why scientists tracking these data sets describe ice decline as capable of accelerating itself rather than naturally plateauing. Now let us travel all the way to Earth's opposite pole. While these developments unfolded within the Arctic, Antarctica has been following its own separate trajectory. For multiple decades, that story looked almost opposite to what was happening up north. This is what confused climate researchers for many years, and it needs proper explanation, because this contrast is key to understanding why current developments feel so alarming to specialists who dedicate their careers to studying it. Unlike the Arctic, an ocean encircled by land masses, Antarctica is a continental landmass surrounded by ocean. This geography matters enormously. For decades, sea ice ringing Antarctica did not follow the warming trajectory observed elsewhere across Earth. While Arctic ice shrank steadily year after year, Antarctic sea ice stayed roughly stable, and in some seasons even expanded slightly. Climate scientists spent years explaining this through a mix of stronger circumpolar winds, frigid meltwater runoff from the continental ice sheet forming a protective layer of colder, fresher surface water, plus the simple reality that sea ice surrounding a large continent behaves differently from floating ice inside a semi-enclosed ocean basin. For a long stretch, Antarctica appeared insulated from the rapid ice loss unfolding in the north. Then in 2016, that buffer broke down. Antarctic sea ice extent, which had trended gently upward or held flat for nearly 4 decades, reversed almost overnight and began sharp, repeated declines. It hit an all-time low in 2022, then broke that very record again in 2023. Ice extent dropped so far below historical averages that the area of missing ice alone exceeded the total land area of Greenland. Researchers were left with a difficult question. What shifted around 2016 that transformed one of Earth's most stable ice systems into one of its most volatile? Another research team from the University of Southampton published findings this year describing what they call a triple whammy, 3 distinct mechanisms stacking atop one another to push Antarctic sea ice into a self-reinforcing downward spiral. First, warming upper ocean waters have eroded that cold, freshwater buffer that once shielded ice from below. Second, wind and pressure patterns circulating across the Southern Ocean have shifted. These connect to the southern annular mode, which has persisted in a positive phase, bringing lower atmospheric pressure over ocean waters near Antarctica and pushing higher pressure systems further north toward mid-latitudes. This configuration strengthens westerly winds circling the continent and correlates closely with unusually warm, wet conditions, especially around the Antarctic Peninsula, one of the fastest warming regions on our planet. Third, deep ocean circulation patterns have changed. Currents are drawing warmer water upward from depth to make contact with ice from underneath, melting it from a direction that used to remain relatively stable. Individually, each of these forces the ice might have withstood. Combined, compounding year upon year, they have pushed the whole system into a state researchers say amplifies its own decline instead of naturally bouncing back. According to the latest monitoring reports, Antarctic sea ice extent sits at the 6th lowest value recorded for this seasonal point. Regional data paints a fragmented picture around the continent. Within the Atlantic sector of the Southern Ocean and marginal seas adjacent to the Antarctic Peninsula, ice retreat has been exceptionally rapid. Meanwhile, areas closer to the Ross Sea remain closer to historical averages, partially cooled by unusually strong southerly outflow winds, driven by an intensified low-pressure system known as the Amundsen Sea Low. That same pressure feature simultaneously pushes warm northerly air into the Bellingshausen Sea along its eastern flank. This explains why you can look at present-day Antarctic maps and see abnormally cold regions sitting right next to unusually warm ones, both driven by that single nearby atmospheric circulation feature. This patchwork regional behavior may sound like a technical detail, yet it directly ties to one of Antarctica's most startling recent events, an occurrence that would have dominated polar news cycles all by itself under other circumstances. In the middle of the 2024 Antarctic winter, when large sections of the continent lie in near total darkness, and temperatures normally sit below -30 degrees Celsius, East Antarctica endured a heat wave outside the bounds of existing extreme event models. Local temperatures spiked as much as 28 degrees Celsius above seasonal averages and stayed elevated for more than 2 consecutive weeks. Researchers studying the event worked to frame this anomaly for audiences who have never visited polar research stations. The comparison they landed on is almost difficult to imagine. A temperature anomaly of that magnitude hitting the United Kingdom in mid-January would push local highs into the mid-30s Celsius, essentially dropping a summer heat wave deep within the British winter. That is the scale of what took place across East Antarctica, and it unfolded during a season where sunlight barely rises at all. Researchers who analyzed this event and published their work this year in a peer-reviewed climate journal concluded this was not random bad weather. It stemmed from multiple overlapping factors: a weakened polar vortex, that ring of cold air that normally seals off the Antarctic interior, an atmospheric river funneling unusual surges of warm, moist air deep inland, plus record-low offshore sea ice removing natural barriers that would normally block warm air from penetrating so far onto the continent. Climate simulations run by that same research team found human-driven global warming substantially amplified both the intensity and duration of this heat event, making such an extreme anomaly far more probable than it would have been under pre-industrial climate conditions. This is the detail that ought to grab people's attention. Researchers explicitly state this was not a one-off fluke. They frame it as a preview, a glimpse of extreme events expected to grow more frequent as underlying warming builds across coming decades. If a sudden winter heat wave feels abstract, the story of one glacier makes tangible consequences hard to ignore. Hectoria Glacier along the Antarctic Peninsula has recently become the fastest retreating glacier documented within modern satellite archives. Over a span measured in months, its grounding line, the boundary where ice transitions from resting on bedrock to floating on seawater, retreated roughly 8 kilometers, with nearly half that collapse unfolding within an extremely compressed time frame. Investigators traced the root cause to underwater terrain beneath the ice. Unlike glaciers sitting on bedrock that slopes upward toward the coast, which naturally slow retreat as they pull back, Hectoria rests atop an unusually flat stretch of seabed that lies below sea level. Once the glacier lost firm contact with that flat bed, almost nothing physically halted its collapse. Massive grounded ice slabs broke free in quick succession, rather than the slow, gradual retreat scientists typically model. Researchers flag this as a meaningful discovery, not simply because of Hectoria's rapid collapse itself, but because it reveals a mechanism that could apply to other West Antarctic glaciers sitting atop similarly flat, sub-sea level bedrock. Several of those hold enough ice to produce meaningful global sea level rise should they behave in comparable fashion. At this point, it makes sense to step back and ask the obvious question any first-time observer would raise. Is our planet genuinely more unstable right now than it has ever been? Or are we simply witnessing serious but expected consequences of over a century-long warming trends playing out simultaneously across two geophysically distinct polar systems? The honest, evidence-based answer sits somewhere in between. We need precise framing instead of jumping to the most dramatic interpretations. The Arctic and Antarctica do not directly communicate with one another. There exists no single physical mechanism linking a northern pole collapse in real time to events down south. They are separated by an entire planet, different ocean basins, distinct atmospheric circulation cells, and completely different geography. One ocean surrounded by continents, the other continent surrounded by ocean. What connects them is not direct physical linkage between poles. It is the same root driver, a planet steadily accumulating excess heat from rising greenhouse gas concentrations, manifesting through whichever local environmental pathways happen to be most vulnerable within each region. Within the Arctic, that pathway is albedo feedback acting upon floating sea ice inside a warming ocean. For Antarctica, it is a more complex mix of shifting wind patterns, eroding cold water buffer layers, and deep ocean circulation shifts acting upon a continent that until fairly recently resisted global warming signals seen elsewhere. We should also directly address arguments that repeatedly surface whenever polar ice and climate trends are publicly discussed. Leaving them unanswered creates gaps in the full picture. Over the years, individual studies and single years within long data sets have shown brief periods of ice recovery at one pole or the other. Those isolated data points are sometimes taken out of context to argue that overall warming narratives are overstated, or that decades-old climate predictions failed to materialize. Some older forecasts did indeed badly miss their projected timelines, and that observation is fair to acknowledge. Yet a short-term public prediction missing its deadline is entirely separate from multi-decade physical trends measured by orbiting satellites. The research laid out here does not rest on speculation or single alarming headlines. It draws upon nearly 50 years of continuous, independently verified satellite measurements cross-checked by multiple national space and ocean research agencies across different nations. Consistently, these records reveal the same long-term directional shift, even when individual years temporarily swing the opposite way. One cold winter or a single year of partial recovery cannot erase a 50-year trend, just as one unusually mild summer afternoon does not undo seasonal change. So beyond ice itself, what practical meaning does all of this hold for people living thousands of kilometers away from either pole? This is where polar changes connect back to everyday life in ways easy to overlook. Sea ice loss alone does not generate large-scale direct sea level rise because floating ice, similar to ice cubes inside a drinking glass, already displaces water before it melts. Sea level risk originates from land-based ice, glaciers and ice sheets sitting atop bedrock such as Hectoria Glacier. Every meaningful acceleration in their collapse translates directly to rising coastlines across our whole planet, not just near Antarctica. Even so, sea ice loss remains enormously consequential, because it acts as one major trigger speeding up all those other processes. Less sea ice creates more open dark ocean absorbing solar heat, extra heat stored within oceans, and atmosphere destabilizes nearby land-based glaciers that do drive sea level increases. Diminished Arctic winter ice reshapes pressure systems that alter storm tracks and cold air outbreaks across the entire northern hemisphere, and the weakened Antarctic polar vortex responsible for that extraordinary 2024 winter heat wave has documented ties to disrupted weather patterns extending all the way into southern hemisphere mid-latitudes. There is one more concept worth understanding. Researchers closely monitoring polar conditions are watching for a scenario they describe for both poles simultaneously, the blue ocean event. This term describes the point when regional sea ice extent drops below roughly 1 million square kilometers. That threshold is low enough that satellite imagery of that ocean basin would show mostly open, ice-free blue water, rather than the expansive white ice cover people associate with polar zones. Specialists tracking current trends note the theoretical possibility that both an Arctic blue ocean event and an Antarctic blue ocean event could take place within broadly overlapping coming year windows, something never observed simultaneously across the satellite era. It is critical to clarify exactly what this term means and what it does not. It does not mean all ice on Earth vanishes. It specifically refers to seasonal minimum ice extent falling under that defined threshold, a regional seasonal occurrence, not permanent total loss of all polar ice worldwide. Even a temporary blue ocean event at either pole would produce levels of sunlight-absorbing open ocean that our measured climate system has essentially never experienced throughout the satellite observational period. And the albedo feedback loop we covered earlier means even such a temporary shift could leave lasting impacts on how rapidly surrounding ice recovers in subsequent years. We also need to fairly address counter-arguments that circulate alongside stories like this. Good explanations should engage opposing perspectives instead of brushing them aside. Antarctica's pre-2016 behavior genuinely puzzled climate scientists. For years, that puzzle got cited, sometimes fairly and sometimes in bad faith, to suggest warming science was less certain than presented. But that early stability never meant global warming was absent. It reflected Antarctica's unique geography and ocean circulation temporarily counteracting warming signals within sea ice, via protective mechanisms including cold meltwater layers and strong circumpolar winds. When those buffering systems began breaking down around 2016, exactly as outlined within that triple whammy research, Antarctica stopped being the exception and began catching up to trends already underway across the Arctic and most other parts of our planet for decades. That pause was real, yet it was not permanent. Understanding exactly why it ended is far more scientifically meaningful than either dismissing it or treating it as proof the whole climate system was fundamentally broken from the start. Zoom out far enough, and both polar stories ultimately illustrate identical underlying physical realities manifesting through two separate regional systems. This is the key takeaway to carry away from this material. Ice systems that look stable for years or even decades do not automatically prove warming pressures have halted. Sometimes they demonstrate local protective mechanisms holding back change temporarily. Those safeguards can and do give way once underlying stress crosses certain thresholds. That stress may build gradually and then reveal itself abruptly, as seen in the Arctic's 2025 sharp decline, or it may accumulate quietly for years before flipping an entire continent's ice trajectory within a single season, as happened across Antarctica after 2016. Scientists watching both poles are tracking several specific indicators moving forward. These are the metrics worth following if you want genuine insight into future developments, instead of only reacting to each new dramatic headline. In the Arctic, researchers will observe whether winter sea ice settles into that lower baseline predicted by recent models, fluctuating without full recovery, or if it somehow stabilizes closer to conditions considered normal just 1 decade ago. For Antarctica, key markers track whether those triple whammy driving forces keep amplifying one another, or if natural variability within the southern annular mode and Amundsen Sea low shifts back toward configurations that give sea ice opportunity to rebuild. Across both poles, scientists watch for that precise combination of conditions that generated the remarkable 2024 East Antarctic heat wave: low sea ice coverage, weakened polar vortex, and unusually active atmospheric rivers. If that same setup repeats, researchers already know what outcomes to anticipate. None of these developments only matter to people living near coastlines or research stations. Weather patterns reshaped by warming Arctic and Antarctic systems touch ordinary lives everywhere, through shifted storm paths, altered growing seasons, plus cold snaps and heat extremes once labeled freak anomalies that scientists now frame as increasingly expected patterns. Grasping actual physical mechanisms behind these news headlines, rather than only fixating on scary raw numbers, separates genuine informed awareness from simple anxiety. That distinction matters, because awareness without real understanding can tip over into panic or get fully discarded the moment a single seasonal data point moves in the opposite direction. The honest takeaway from research published this year is not that polar ice is collapsing overnight in some sudden world-ending catastrophe. Rather, two enormous complex natural systems, each enjoying decades of relative stability, have simultaneously entered well-measured, mechanistically understood periods of decline. Their local triggers differ, yet they trace back to shared root causes. This is not certainty disguised as prediction. It is what nearly 50 years of consistent satellite observations cross-validated by independent research teams across multiple countries show us within the data itself. It helps to contextualize our measurement tools, too. Confidence in everything laid out here rests upon the quality of instruments capturing these changes. All Arctic and Antarctic figures referenced come from microwave radiometer sensors aboard multiple satellites. These include instruments jointly operated by Japan's National Institute of Polar Research and Japan Aerospace Exploration Agency, alongside NASA and the United States National Snow and Ice Data Center. These sensors do not rely on visible light, meaning they measure ice extent continuously through total polar winter darkness and heavy cloud cover, conditions that would render conventional photography useless for months on end. That all-weather continuous coverage is why the dataset stretching back to 1979 ranks as highly reliable. That is also why a 6% single-year Arctic drop or Antarctica's 6th lowest seasonal reading are treated as precise cross-validated figures, not noisy, uncertain guesses. Multiple independent institutions across different nations arrive at matching results and cross-check against one another. When separate research groups using different satellites and processing workflows converge on identical findings, that represents observational science near its strongest outside laboratory settings. Bear in mind as well that this satellite record, long as it feels, spans only 47 years, a mere blink within geological time. Every record broken in 2022, 2023, 2025, and 2026 is not just a record within living memory. It represents the lowest values ever captured by direct instrumental measurement, full stop. We possess no equivalent pre-satellite baseline for direct comparison, which explains why researchers keep reaching for words such as unprecedented instead of merely unusual. What comes next will hinge upon decades' worth of human choices still being made today, just as always for climate trends that build slowly and then manifest all at once. Scientists will keep flying survey missions across these regions, deploying instruments within ice, and keep publishing whatever data reveals, whether findings turn out more reassuring or more alarming than present-day knowledge. If you want to stay updated as these two narratives unfold, whether the Arctic locks into its new lower baseline or Antarctica's triple whammy forces keep compounding, subscribing ensures you catch new updates the moment fresh research emerges. Sharing this material with people who still believe both poles are simply bouncing back on their own is one of the most useful things you can do in the next 30 seconds. Drop a comment telling me which development surprised you more: the Arctic's abrupt crash after 20 years of apparent calm, or Antarctica's gradual reversal after decades looking like Earth's one stable holdout. Either way, both ends of our planet have recently demonstrated stability, and permanence are far from the same thing. And the ice-keeping score of that distinction pays no mind to whether humans were paying close enough attention to notice in time.